Hello, we are the University of North Texas 2024 NASA Big Idea Challenge participating team. We are proposing our Wave-Operated Robotic Movement System, or WORMS.
This year's NASA Big Idea Challenge deals with the topic of inflatables, focusing on low size, weight, and power consumption. Students are encouraged to find innovative solutions which enhance lunar exploration and habitation, promote long-term sustainability for lunar operations, and improve lunar infrastructure, promoting the well-being and efficiency of astronauts living and working on the moon. WORMS, or Wave Operated Robotic Movement System, is an innovative, inflatable soft robotic conveyance system designed to move material from one point to another on the lunar surface. It aligns with Artemis's program goals for sustainable lunar exploration using low size, weight, and power modules. It is also designed to aid in NASA's mission of in situ research utilization.
For our calculations and cost overview, as you can see, we have split it up into two component categories in our bill of material. We have our system and our structure. The system comprises mostly of our all of the little components that we need in order to signal all of the bladders to move sequentially down the line, whether that be all the wiring, relay, such and such, in order to interface with our Raspberry Pi that signals all this stuff to work, as well as all of the pneumatic tubing and connectors and such and such. Our structure, on the other hand, where most of our cost comes from, is just our material for our outer cover and our bladders in order to house everything. As you can see, it is kind of expensive, but at the same time, we are well within our budget. As for calculations, we've really boiled it down to two different equations, that being minimum pressure that we need is just our load that we're trying to move, times the surface area of our sled that's interfacing with our bladders. That's just the minimum pressure we need to overcome in order to move. And with that being said, we also need to take in consideration our frictional force between our sled and our actual outer cover of our bladder in order to make that as smooth as possible with as little resistance.
With efficiency and logistics in mind, the capabilities for our system are based on the mechanical phenomenon known as peristalsis, where a series of synchronized and controlled movements like a wave aid in propelling material along. Our soft robotic system is designed to be compact and lightweight, making it convenient for packing, stowing, and transport. We address the requirement for a readily deployable and adaptable system by our modular inflatable bladders and QD design implementation.
The controls for the wave-operated robotic movement system is designed to manage a series of 8 inflatable valves, utilizing a total of 16 normally closed solenoid valves, 8 for inflation and 8 for deflation, to facilitate a wave-like motion capable of propelling objects forward in a conveyor-like fashion. The valves are connected to a Raspberry Pi, which orchestrates the sequential opening and closing of valves to precise timing control, allowing for inflation and subsequent deflation of bladders in a coordinated manner. This programmable approach ensures flexibility, enabling the system to handle different object sizes and weights with ease, while also providing a straightforward method for scaling or modifying the system in response to specific requirements. Safety measures, including an emergency stop function, are integrated to rapidly deflate all bladders in case of malfunction, ensuring the system's safe operation.
Here we have the new WORMS assembly with an exploded view. This design is expected to be about 4 feet long and 2 feet in width, with 8 bladders about half a foot in width each. There's a sled that will contain about 1 cubic foot of volume that will be used to transport the material. Over in the exploded view, you can see, starting from the top and moving down, we have the solenoid valves. These will be programmed to allow pressure in and out of the bladders. One step below that, we have the pressure tubing system, obviously directing the air from the compressor and air reservoir to the bladders through the solenoid valves. Underneath that, we have the sled that we have spoken about. Underneath the sled, we have our 8 bladders that will inflate and deflate in a wave motion directing the sled. And last but not least, we have the overall WORMS cover, which will contain all of these components, and it's designed with the ridges to keep the sled in place.
The Gantt chart that we submitted for the NASA 2024 Big Idea Challenge was broken up into 2 phases. The first phase centered primarily around the procurement of materials and the assembly of our worms conveyor system, and was supposed to last from February of 2024 to June of 2024. The second phase centered around the demonstration of our conveyor system and was supposed to last of June 2024 all the way to November of 2024. Due to the change in the competition, we have updated our Gantt chart to consolidate all tasks to be completed by the end of this semester.
For our simulations, we decided to do a variety of static load simulations utilizing low lunar gravity to find deformation and stress testing. We compiled a variety of resultant reverse normal force vectors from the simulation to help us determine the necessary pressure we would need to apply from each of the bladders onto the weight of the material sled. We did this for all 8 sections and each bladder in each section. The simulated load we applied was from 30 to 50 pounds through the material sled container, and this was through around a 10-inch by 10-inch material surface area that the bladder would meet when in contact. The outer canvas cover was made of our polyvinyl chloride fabric, and the material sled was made of some printed PET plastic. The motion study segment of our system uses both a deployment and operation phase. In the deployment phase, we opted for a retractable rollout and inflating system that can be stored compactly and activate for use with the connection of both electrical power and pneumatic pressure. We designed the system specifically to move our design material container sled along the length of the system, using pneumatic air pressure, which would displace the sled sequentially between each of the bladders. Additionally, multiple worm segments can be connected together to extend the conveyance system over longer distances.
This updated design utilizes fewer mechanical components, resulting in easier assembly. The assembly starts with the inflatable bladders, which are then connected to the pressure and electric lines, which are governed by the solenoid valves. The outlet connections are hooked up to the compressor, the Raspberry Pi is installed, and then the entire system is wrapped in the expansion cover. The material container is placed on the conveyance system, and the system is ready for operation. For manufacture, we have consolidated parts and chosen cheaper and more available materials for the parts. For the outer cover, we have changed from Kevlar to thin PVC fabric, similar to the material used in air mattresses, but the method of manufacture remains the same in cutting, sewing, and gluing with rubber cement. The bladders remain unchanged, using a neoprene elastomer material, using sewing and gluing with rubber cement. The pressure lines will no longer use fluorosilicone, but instead will use standard high-pressure silicone tubing due to price concerns for the prototype, but both should be feasible for a production model. Silicone tubing is usually produced by thermosetting. The electrical lines will no longer be high-grade space wire, but standard electrical wiring for the prototype due to cost concerns, produced by wire extrusion and coated in plastic. The material container requires a low friction coefficient and must also be high strength, so polyethylene terephthalate was chosen for the material. For our DFC, we worked to reduce costs for prototyping to provide proof of concept and still maintain funds in case design changes needed to be made later in the production process. The simplification consisted of a redesign, an elimination of many superfluous parts, simplification of parts, and change of materials for less costly alternatives. All our parts will be ordered from manufacturers, and no parts will be made in-house due to the relative complexity of the system and components. However, we will be assembling the outer cover and bladders. This redesign has reduced the price of the old model from approximately $2,708 to about $1,420, approximately half the price, while still being able to accomplish the same design parameters.
This concept from the beginning has been unique, and we saw real potential benefits for NASA's lunar missions, which is a testament to the creativity of the idea. As with any innovation, we needed more research and development, a more intensive plan to address things like material degradation and testing. We have unique critical conditions with an environment as challenging as the moon, which is of course difficult for our team to replicate. The Challenges Judging Panel's feedback pointed out the complexity of our proposed concept over a more conventional system, showing how innovative yet ambitious our concept was. Reflecting on this feedback has allowed us to regroup and mitigate the risk going forward by refining our design.
In response to the feedback we got regarding our proposal, we created a number of changes to our design. Two of them being we now are going to produce bladders that are accordion style, which will cause ease of movement within the conveyance system. The second is we changed our outer cover to be polyvinyl chloride. Testing will be performed to observe how well the material suits the project's needs.
For the remaining semester plan, there's a few things that we'll need to complete. First is to finalize our new revision. As you can see in the previous slides, we went from our old rev to a new rev. With that, we'll need to update our prints and documentation to match that. With that, we'll start to work on the prototype, work on the manufacturing of it, and find what maybe some issues with manufacturing can be. Once that's been complete, we'll test the prototype to make sure it works how we want it to, and find any things that we need to fix and can improve on. And once that's been completed, we'll create our final product that should meet all of our criteria and requirements for our final product for the senior design.